Archaeoastronomers have found 3 types of early observatories: simple markers, circles of stone and wood, and temples. Early on, markers were used to create sight lines to the horizon, so that during the equinox or solstice, the sun would appear to rise exactly on the sight line. Stonehenge in England was set up this way, as were a number of ancient Native American buildings, such as the ones at Chaco Canyon in New Mexico and Hovenweep in Utah. England's Stonehenge is one of the earliest examples of an observatory in Europe. Stonehenge is a large calendar capable of predicting the equinoxes and the solstice. Before Stonehenge, in 3000 BC, the ancient Egyptians had devised a solar calendar of 365 days, the starting point of which hinged on the heliacal rising of the star Sirius, which also happened to coincide with the summer solstice and the annual flooding of the Nile. By being in touch with celestial phenomenon and their natural surroundings, the ancient Egyptians were able to predict events of great significance in their desert environment. At Abu Simbel, massively carved statues of Ramses the Great face east to greet the sun god Re, the bringer of light. As the sun rises each day, the statues are illuminated again, perhaps a sign of rebirth for Ramses. But the most compelling is a passage to the temple's inner sanctuary, which is aligned so that on October 18th, the sun filters into the sanctuary, illuminating a statue of Ramses. While October 18th doesn't mean much to us in the Western world, this October date corresponds to the beginning of the Egyptian civil year and the celebration that occurred during the time in which Ramses lived.
It was the Greeks, however, that created the first portable cosmological tool for keeping track of these motions: a stick. The Greeks actually called it a gnomon, and it was used to keep track of the shadow of the sun. Actually, it's a little bit more difficult than that because the shadow depends on your latitude. Again, if you are not near the equator, the shadow will be shortest during the summer solstice and longest during the winter solstice. For the spring equinox and fall equinox, the shadow will be halfway between the shadow lengths at the solstices. In the southern hemisphere, the shadows will be reversed, just as you all know the seasons are reversed. When it's summer in the United States, it's winter in Argentina. This all works pretty well if you're not at the equator. At the equator, the summer solstice sun casts a shadow in a southerly direction, and the winter solstice sun casts a shadow in the northerly direction. During the equinox, at the equator, the shadow disappears. Oh, and another thing that they were used for is sundials. And it looks to me like it's time to go back to Jennifer.
Okay, guys, let's take a look at how a gnomon works and see the angle of the sun at certain times during the day. Students from Newcomb Elementary School in Newcomb, New Mexico will preview this show's hands-on activity.
Yes, hello. We are students from Newcomb Elementary School. We are located in the Navajo Reservation in the Four Corners region of New Mexico. Tracking the passage of the sun in the sky continues to play a very important role in the life of our Navajo culture.
Traditional Navajo still use this system of tracking the sun's shadows to tell time and to tell the changing of the seasons. For example, when my grandfather herds sheep, he does not wear a watch like this. He uses the sun's shadow to tell time. It also helps him to tell when to take the sheep back home in their corral. It also helps him to tell when to plant corn and watermelon on his farm.
NASA Connect asked us to show you this program's hands-on activity.
In this activity, the students will make sun shadow plots every half hour, marking the ends of the shadows made by the sun and a gnomon.
You can download a copy of the Educator Guide from the NASA Connect website for directions and a list of materials.
Turn a cardboard box upside down. Tape a large piece of paper to the cardboard box. Draw 2 lines that are perpendicular to each other, from top to bottom, and the other from left to right across the paper. Mark its center with a dot. And make a very small hole in the center of the box using the point of a scissors. Stick the gnomon through the dot and the hole in the cardboard. Secure it with tape so that 10 centimeters is sticking straight up out of the box. Use a protractor to make sure the gnomon is perpendicular to the box. On a clear sunny day, find a large flat area. Tape the box to the ground on all 4 sides. Starting as early in the morning as possible, mark the end of the gnomon shadow every half hour until the end of the day. Next to the dot, label the time of the day it was marked. You will analyze the data you collect by measuring angles and length. Remove the gnomon and draw a straight line from each dot to the hole that the gnomon was placed in. Measure and record the angle between the horizontal line drawn through the center of the paper and each marked shadow. Then, measure and record the length of each shadow. Using geometry, find and label true north on your sun shadow plot. Verify local solar noon using shadow length times and sunrise-sunset times. How do the lengths, positions, and angles of the shadows change? What do the changes tell you about the position of the sun throughout the day? Would the curve change if you used a different-sized gnomon to cast the shadow?
And don't forget to check out this cool web activity for this program. You can download it from the NASA Connect website.